Welcome. Today we are diving into the topic of frame allocation. Frame allocation is a crucial concept in operating systems, especially when dealing with memory management. In this session, we'll explore how operating systems allocate memory frames to different processes, ensuring efficient and effective use of available memory resources. Frame allocation is the method of deciding how many frames of physical memory to give to each process in a virtual memory system. Frames are like fixed-size blocks of physical memory, and each process needs a certain number of them to run smoothly. The way these frames are allocated can greatly affect how well the system performs. A good allocation strategy is crucial for avoiding a situation called thrashing. Thrashing is a condition where the system spends more time swapping pages in and out of memory than executing instructions. So, allocating frames properly helps in preventing this issue. Every process has a minimum number of frames it needs to run correctly. This number depends on the specific instruction set architecture of the processor. The allocation must account for the worst-case scenario, that is, the maximum number of frames that might be needed at any given time. Ensuring that a process has at least its minimum required frames helps to avoid excessive page faults. A page fault happens when a process tries to access a page that is not currently in memory, causing a delay as the operating system retrieves the page from disk. For example, consider an instruction: add memory address 1, memory address 2. This single instruction might need to access multiple pages in memory to fetch the instruction itself, as well as the data at the specified addresses. Therefore, at least 3 frames are needed to execute this instruction without immediate page faults. There are a few different ways to allocate frames, each with its own pros and cons. Let's discuss 2 common methods. First, there is equal allocation. Equal allocation is straightforward. It divides the available frames equally among all the processes in the system, regardless of how big or small they are. For example, if we have 100 frames in 5 processes, each process would get 20 frames. Then there is proportional allocation, which allocates frames based on the size of each process. Larger processes get more frames than smaller ones. For example, if the processes have a size ratio of 1:2:3, and there are 60 frames available, the processes would get 10, 20, and 30 frames respectively. Priority-based allocation involves giving more frames to higher priority processes. This approach aims to improve the performance of critical processes by ensuring they have enough memory to run efficiently. It is often used to ensure that foreground processes, which are the ones the user is actively interacting with, get preference over background tasks. Priority allocation can be combined with proportional allocation to fine-tune the distribution of frames based on both size and importance. Be careful, though. This allocation method can lead to starvation of lower priority processes. If the system isn't managed carefully, lower priority tasks might not get enough frames to run properly or at all. Frame allocation strategies can be either global or local. In global allocation, frames are taken from a shared pool of free frames, which means any process can potentially use any frame. When a page needs to be replaced, the operating system can choose a frame from any process in the system. This can lead to higher system throughput and better memory utilization, since resources are used more flexibly. However, it can also cause a process's performance to vary unpredictably. Local allocation, on the other hand, limits each process to a fixed number of frames. When a page needs to be replaced, the operating system only considers frames that are already allocated to that process. This leads to more predictable performance and better isolation between processes, but it might result in lower overall memory utilization. In global allocation, a pool of free frames is available to processes A, B, and C. In local allocation, each process is assigned a fixed number of frames. The working set model is a dynamic approach to frame allocation. It allocates frames to a process based on the pages that the process is actively using. The model tracks which pages a process has accessed within a certain recent time window and tries to keep those pages in memory. This method adapts to a program's locality of reference, meaning it focuses on the pages that the program is currently working with most frequently. It helps to prevent thrashing by making sure each process has enough frames to accommodate its current working set. The working set is defined as the set of pages that a process has referenced in the last delta time units. Let's recap the key points of frame allocation. First, every process needs a minimum number of frames to execute, based on its architecture and instruction complexity. Then, allocation strategies like equal, proportional, and priority-based allocation help to distribute frames among competing processes. Global allocation allows processes to share frames from a common pool, while local allocation limits processes to their own assigned frames. Finally, the working set model dynamically allocates frames based on the pages a process actively uses within a given time window. In conclusion, effective frame allocation involves balancing system performance, process requirements, and the available physical memory. The goal is to minimize page faults and prevent thrashing, ensuring the system runs smoothly and efficiently. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.